When we received the Threadripper 3990X on loan from a yet unnamed YouTuber, we quickly threw together an extreme overclocking stream and got the CPU to about 5 GHz with bearded hardware and on really zero notice. Since then, we've been working on adding some new testing, like a revisit of code compile benchmarks, and we've put together a full review of the 3990X. The AMD 64-core CPU is tough to benchmark. At $4,000, it's also an uncommon purchase for most of our audience. But it's still interesting from a perspective of seeing how the ultra high-end components scale in software. The 3990X isn't an easy benchmark since it begins nudging towards server workloads, which we don't test. But we still have a full production suite of benchmarks for the 3990X to see how it does in other applications. Before that, this video is brought to you by Thermal Grizzly's Conductonaut Liquid Metal. Conductonaut is what we've used in all of our liquid metal and delid thermal tests, capable of dropping CPU thermals significantly when replacing the stock thermal interface. Lower CPU thermals don't just allow better overclocks, but also lower noise levels because the transfer efficiency is increased. The mix of gallium and indium makes for a thermal conductivity of 73 watts per meter Kelvin, outclassing traditional pastes significantly. Learn more at the link in the description below. So first off, we're just throwing this together before going to Taiwan. It's a pretty complete review by our normal standards in that it's got all the tests we would do for a 3970X. But the 3990X does sort of ask for a couple of new tests. So we've added the code compile test for this one. We're not really ready yet to talk about the full new methodology overhaul. We do this every year around this time where we convert everything to new testing methodology, new software, new benchmarks, all of that stuff, new games. But we're not ready to talk about it just yet, except we've pulled the code compile test, which is Chromium. It's done on Windows, at least for now, and we're using that as our new tool for the 3990X. And it was actually a very interesting one to test with a 64-core CPU. Other than that, we have the standard set of things that we test for everything, which would include Adobe Premiere, Photoshop, which everyone I think knows will not really particularly scale well with the Threadripper CPU in general, but we have Premiere on there, which has scaled reasonably so far. And then we've also got tests like compression and decompression, which are interesting ones that show scaling in some places and not in others, and a couple of other ones to look at. Blender, for example, for a tile-based rendering application. So that's what we've got to start with. There's more that we'd like to do with this CPU as well, like another overclocking stream, an XOC stream, and then maybe a chilled water stream, something like that. It'd be a lot of fun to do with it. And then we've got some other production workloads that we'd like to run specifically on the 3990X, but all of that's gonna have to wait till we get back from Taiwan because we're trying to cram everything together now before we leave. Another quick note here. So we won't really have much of a gaming focus here. That should be predictable. But the one reason we do still include some gaming benchmarks for stuff like this and the 3970X and the 3175X is because specifically what you're testing for is not how well does it play games, but does it play games well enough. So when we have gaming benchmarks for these types of CPUs, it's not to see is it at the top of the charts, because it's not going to be. A 9900K will be in every instance currently. So that's not why the game benchmark's there. It's really just to see if, unlike a 2990WX, you might be able to run the games without severe issues like stuttering or just black screens where it doesn't even work. And the older Threadripper chips had a lot of problems with that. Going to try and work with the 3990X more after our trip, but for now, what you need to know, it's a $4,000 CPU. The 3970X is about $2,000 or so. It's supposed to be $1,700 to $2,000. The 3960X is a fair bit cheaper. The 10980XE cheaper still at about $1,000 in theory anyway. And then the 3950X, which is a very good CPU if you don't need the PCIe lanes and you don't need quite as many cores, is in the 750s. So we're going to be looking at a $4,000 part today. Almost no one in our audience will buy this type of thing, but if you are buying it, really the main competition you're looking at least that's unlocked, is the 3175X. We have that in our legacy charts, which we'll be running today, not in the code compile chart though, and that's a 28-core CPU, which ranges in price these days, $1,500 to $3,000, depending where you check and when, and the boards are completely ridiculous to buy too. One of the only ones on the market is the SR3 Dark, and that's like $1,800. So even that ends up costing a bit more than the 64-core option from AMD. And finally, I'll give a quick shout out here too to two others. If you're interested in the Linux side of things, Linux testing, I know there's going to be interest in that for this part. We're simply not going to do it for today, maybe in the future, but there's not enough time right now before a trip. If you're interested in it, check out Phoronix or TechGauge. Both of them have Linux tests. They're very in-depth, and we'll leave that to them for now. All right, so let's get into it. We'll start with the newer test, we'll look at some code compile, look at how frequency scales across various thread intensities for workloads, some thermal numbers, which are very interesting for this one, and then we'll go through legacy benchmarks for the workstation applications that we have for now. Our first test from the new suite is our compile benchmark, which has been widely requested. We previously introduced code compile testing with GCC, but we scrapped it and have instead introduced compile testing with Chromium build time. We'll talk more about the specific testing methodology and the parameters in our formal methodology unveil video after our trip to Taiwan, but we wanted to show this in advance for the relevant 3990X comparisons. This chart doesn't have many parts on it yet, but we have other charts that are more detailed later on. For this one, the 3990X shows direct scaling and isn't held back before it's able to leverage the cores. We did find that the CPU really needs a lot of RAM for this though. 64 gigabytes seems to do the trick. Our standard 32 gigabyte configuration was paging out to the drive and massively slowing down as a result. The CPU in this RAM constrained scenario is too fast for its own good if it doesn't have enough memory and will actually perform worse than a 10900X. With the bottleneck removed here, the compile time with 64 gigabytes of RAM comes down to 22.3 minutes compared to 31.6 minutes on the 3970X 32-core CPU. That's a time reduction of 29%. So it's not a linear reduction, or even really that close to a linear reduction, but it's not bad overall. Against the 10980Xe 18-core CPU, the 3970X improves by over 20 minutes of difference, reducing compile time by 43%. The improvement to the much more expensive 3990X is about 60% less time required, although we'd like to see more price comparative benchmarks soon, and we'll do that once we get back. We can add the 3950X to these charts once we return, and for reference as well, we ran the test on the 10900X with 64 gigabytes of RAM and noted that there's no meaningful uplift. It only starts to matter with the 3990X for this one. The 32 gigabyte RAM allowance is not exceeded by anything except for the 3990X. It'd be worthwhile next to demonstrate the frequencies of the 3990X under a few different circumstances, as well as the temperature. We'll start with a single-threaded maximum frequency. Running Cinebench R20 single-threaded against the 3990X, the CPU ended up holding about 4325 megahertz on average, with peaks at 4350 megahertz single core and dips down to 4300 megahertz, ignoring one fall to 4275. During workloads of limited thread count, this is where you can expect the frequency to rest for a single core load, like Cinebench R21T. We next ran a multi-threaded benchmark just for fun. Let's produce a completely useless chaotic chart with 64 lines on it on the screen to sort of illustrate the illegibility of data we were dealing with. If you feel overwhelmed looking at this, that's how we felt when first looking at the log file after the first time of working with a 64-core 128-thread CPU. One useful thing does come out of this though, and that's the average all-core frequency that we can plot on a new chart. The average clock across all cores is about 3130 megahertz to 3160 megahertz, with the maximum single-core boost during this time typically being 3800 megahertz, which spikes to 4000 megahertz occasionally. A quick thermal test is next. This one is really just to establish what level of cooler is expected to keep the 3990X in check. We aren't doing a comparative test versus any other CPUs for this, so it's just a one-off to give an idea of cooler needs. For this one, we're using a refurbished Enermax Liqtech 2 360 that we've drained and refilled. It doesn't have gunk in it, and so this one is one of the good ones. Remember that the Liqtech series is actually one of the best solutions for Threadripper when it comes to straight performance, but that changes if gunk develops in your cooler. So for straight performance, if it's working well, this is a good solution. It's just not something we recommend purchasing at this point. But if you have one and you can clean it, refill it with a better liquid, then it's still a good option. So the 3990X is interesting for thermal data. The hottest CCD read about 61 degrees Celsius at steady state in a 21 degree ambient environment. The first CCD reported an average T-die of 58 degrees at steady state, with the next CCD about in line with the average, but the third CCD plotting a significant CCD to CCD delta in temperature. The next two CCDs plot one in the lower ranks down below 50 degrees and one in the upper ranks just above 60 degrees. Ultimately, at the end of the chart, we end up with about half the CCDs in the cooler class and half in the warmer class of results. This likely has to do with positioning of the dies, and also keep in mind that each CCD has 8 cores in it, and we can't see the individual core temperatures with AMD like we can with Intel, so we're getting an aggregate with the CCD temperatures. So either way, this could be an instance where lapping the IHS could have meaningful decreases in the core-to-core deltas, We previously showed this in our 9980XE lapping benchmarks, and it should carry over similarly here because that temperature delta CCD to CCD is typically representative of a difference in depth of the IHS. Blender is our first workstation application from our legacy benchmarks, although this one's carrying over to the new stuff too because it's so good. Blender spawns one tile for every thread on the CPU, which means that Threadripper and the 64 cores of the 3990X scale in a predictable fashion, but not quite linear, versus the 3970X. For our more intensive GN logo render in Blender, the 3990X requires 4 minutes to finish each frame, a reduction of 37.5% time required from the 3970X's 6.4 minute requirement. That's also a reduction of 29.8% versus the overclocked 3970X's result. A 100% increase in cores obviously doesn't get you a 50% decrease in render time, but at almost 38% stock to stock, it's pretty damn close when considering all of the other changes in the CPU aside from just the cores. Compared to the 3175X at 9.3 minutes, the 3990X finishes the render in about 57% less time. The 3175X has an advantage in overclocking, but that's only enough to get it past the stock 3960X and to begin approaching the stock 3970X. As for Intel's more commonly available 18-core CPU, the 10980XE finishes in about the same time as the stock 3175X when the 10980XE is set to 4.9 GHz. Ours was a really good chip, but it requires 14 minutes when fully stocked, putting it just behind the 3950X. You'd be better off with a 3950X if you don't need the PCIe lanes, and if you want to spend less than, say, $2,000 to $4,000 on a processor, this is probably your next best choice. For quick reference, we also ran our logo render on the primary production PC we use in the office, except using CUDA only. It's not a like for like, it's intentionally different. That resulted in a 2.8 minute render time with the Tesla V100 GPUs. For our Blender GN Monkey Head render, the stack shuffles a bit and changes from a result of our test design. But this isn't too different for the HEDT parts. The 3990X requires 3.7 minutes per frame to render this animation, with the stock 3970X CPU at 5.6 minutes for its render time. That's a stock-to-stock reduction of 34% render time, benefiting the 3990X. Overclocking the 3970X reduced its render time by 5.3%, but significantly increased cooling and power requirements, so we don't really think it's worth it. The 3990X requires 46% less time than the 3960X, furthering that it's not one-to-one scaling with cores in Blender, but that there are still improvements to be had. We can next cover a common workstation application that's less likely to care, but has been growing to support increasing core counts over the past few years. Using Adobe Premiere and Adobe Media Encoder to render our 1080p convention floor report, the AMD Threadripper 3990X CPU illustrates that we've encountered an immediate limitation of scaling against the Threadripper CPU. Intel's 3175X is a technical leader here, but it loses in value, and we don't really recommend the processor given the combined board and price and limited victories in benchmarks. We already talked about this one in our 3175X revisit from a few months ago, where we generally recommend the 3970X instead. Stock, the 3175X currently leads the 3990X by about an 8% reduction in total time required. More appropriately, it's about tied with the 3970X, which leads the 3990X by marginal marks. In this test, the 3990X's additional core count isn't helping it, and the higher frequency parts at or below 32 cores have the advantage. More cores isn't always more better, but in some applications, it will be. Blender was one of those, and we have others coming up. To finish Premiere first, our 4K 60 B-roll render shuffles the deck a little bit, but not by much. The 3990X ends up a worse performer than the 3970X or 3960X CPUs. The 3175X completes in about 5.7 minutes or 5.1 when overclocked, with the 3970X completing the render in 6.1 minutes or 5.9 when overclocked. Overclocking Threadripper really isn't worth it for these applications. The 3990X is between a 9980XE and 3970X, and you probably shouldn't buy the CPU just for doing similar Adobe Premiere video production workloads to us. There are cheaper, better options like the 3970X or 3960X. The 10980XE ends up a bit behind the 9980XE, which is at least partially thanks to vulnerability mitigations baked into the silicon. The biggest improvement has been against the 2990WX, which was one of the worst CPUs we've worked with for applications like Premiere, largely thanks to memory latency issues, but we talked about that resolution in the 3970X review. For another legacy test, our compression and decompression results demonstrate clean scaling across the CPUs and also help show memory bandwidth limitations on some products. Starting with compression, we can see where the Threadripper CPUs begin to trip over themselves and choke on memory bandwidth. Intel's 6-channel 3175X pulls far ahead, while the 3970X, 3960X, and 3990X are all right around the same mark due to architectural bottlenecks. They are clearly limited here. The 3990X doesn't offer any compression advantage in this particular workload versus the 3970X, but the 3175X stock CPU runs about a 12% increase in millions of instructions per second over the average Threadripper 3000 series part. Overclocking the 3175X provides a scaling benefit of 9%. In this scenario, Threadripper is limiting itself and has no room for improvement, so it won't be until AMD modifies its memory architecture or channeling again until we see a jump in Threadripper performance for this benchmark. Decompression is a different story. In this workload, the 3990X runs just ahead of the 3970X stock CPU. Our current belief that this is a result, the closeness that is, of the frequency deficit in exchange for cores, at which point we may be encountering diminishing returns, because once you look at run-to-run variation, they trade places in some runs. But overall, the decompression performance of Threadripper is extremely strong as a comparative against the other parts versus the previous chart, and looks good against Intel's parts for this one. We had to expand the chart scale just to accommodate Threadripper, which is always a good thing for the CPU, but a bad thing for legibility. If there's one production workload we can rely on for not scaling against cores, it's Adobe Photoshop. For this testing, we've noticed that the application scales most directly with frequency, not core count, and that's always easily demonstrated by highlighting the 9900K and 9700K both at 5.1 gigahertz, where no benefit is visible. The 3990X, unsurprisingly, doesn't do particularly well here. It's capable of running Photoshop workloads, just like it's capable of running gaming workloads, but it's also about equivalent to a 10900X 10-core CPU, a 9700K 8-core CPU, or a 3900X 12-core CPU, and the 12-core is within error of its own overclocked counterpart for this one. If you're only doing Photoshop workloads like heavy filters, transforms of large images, smart filters, or similar effects, then you should be buying a 9900K. The 10980XE with an overclock would be a good fit for a heavy Photoshop user who also needs some more cores for other workloads, but you're really not buying a 3990X for this. And before anyone cries about, well, why did you even test it with Photoshop then? We don't remove things from our benchmarks for any other parts, so we're not going to do it for AMD's 3990X either. At the end of the day, this does help illustrate that more cores doesn't always just get you chart-topping performance, because that belief is what will cause people to waste a lot of money if they're buying, for example, only for Photoshop. The last of our legacy tests is VRay, which closely and unsurprisingly mirrors the performance of Blender. The 3990X 128-thread CPU ends up at a render time requirement of 13 seconds, a reduction of 30.5% from the 3970X at 4.25 gigahertz, or a reduction of 35% from the stock 3970X. As a refresher, Blender showed us about 34% to 38% render time reduction, so this is in line with what we'd expect. The 3175X manages to mostly keep up with the 3970X's 20-second render time when running at 4.1 gigahertz, but falls behind at stock. So that's the 3990X. Overall, the CPU is in a class where it's difficult to make commentary on value. You can, of course, always do it. The 3175X, for example, is poor value. The 3990X, for a lot of people, would also be poor value, because most people not only don't need a CPU with this many cores or threads, but will also experience regression in performance because you are trading things off for that extra core count and all the threads that the 3990X has. So this is a scenario where these people probably exist more so than genuine users of a 3990X or a server like Xeon type part. The people who buy this, or who I'd caution against buying it anyway, might be the type who just want a really expensive part because they have a lot of money to burn. There's nothing wrong with that, and they just want the best or the highest end computer or whatever. But if you are that person, just be aware that in a lot of applications, like standard applications, a 3990X is not going to be better. So if you have specific workloads, like certain types of file compression or decompression workloads, although you get bottlenecked with some of those as you saw in these charts, or if you maybe do tile-based rendering, at which point the 3990X is actually extremely competitive with even GPU rendering, and it can have more memory than GPUs do, so that's a benefit too. Or if you do things like code compile, those are areas where we've seen a clear uplift, and other benchmark sites that focus more on Linux or Workstation would show you even more still. But a lot of stuff won't show an uplift, so don't just buy it because it's expensive and you want to sort by highest price and add to cart. That's not a good way to build a computer when you have stuff like this out there. There's probably better choices for you if you don't know you need those threads that the 3990X has. If you're more on the enthusiast side of things and you still want this CPU, either for competitive overclocking or because you actually need it for whatever you're doing, one of the enthusiast type things you could look into would be potentially doing some IHS lapping. Now, that does void the warranty because when you send it back, they're going to know that you modified it unless you save all the nickel dust and then glue it back on. But IHS lapping here, we saw working with Joe on the 3970X, would be the same idea, a significant uplift in the consistency of the thermals across the chiplets with lapping the IHS. You're not necessarily going for a direct massive gain in thermal performance. There will be one, but in a lot of cases it's not really anything. A lot of people will probably end up sanding the thing for hours and then go, really, that's it? But you're looking more for a reduction in the die-to-die or the CCD to CCD deltas. So that's a project you could do that would have some benefit here, as we've shown in the CCD thermal charts. They are about 10, 15 degrees different sometimes. That's a lot better than we've seen with core-to-core deltas on the 9980XE, but we can't see core-to-core here, only CCD to CCD. So that's a project you might like. Now, finally, on the workstation side of things, I also want to mention a lot of people, whenever we have the 3175X in charts, think that they're being super clever by saying it's not fair to benchmark an Intel server part, a Xeon CPU, against an AMD non-EPYC part. Shouldn't you be using EPYC for that comparison? The answer is no. The 3175X, that X at the end of it is important. The Xeon W-3175X is billed as an enthusiast part. So it was marketed as an enthusiast overclocking unlocked part. That's the goal of the chip. It's not targeted for server users. It's targeted for workstation enthusiasts, like a hybrid of the two. So just because it says Xeon doesn't mean it's server. EPYC's a bit of a different story. You don't have to be server with EPYC either, but it doesn't quite work that way. So it's a fair comparison, and it's certainly a fair price comparison. And ultimately, it doesn't matter because we're not recommending the 3175X in almost any use case anyway. It's just not good value, especially with the motherboard price factored in. So you're left with basically choosing between a 3970 and a 3990. And for most people, if you're genuinely a workstation user, a 3970 will get 90% of the performance in a lot of the applications. It might perform better in some applications. And then there's a select few, like Blender, tile-based renderers, or maybe code compile, where you start really showing a difference, but it's not a linear one-to-one scale. You don't get a doubling of performance because you've doubled your cores. And hopefully our charts will help you determine if it's worth spending the extra $2,000. Ultimately, it's probably going to come down to the question of, do you make money with your computer? And if you're doing one of those applications where the scaling is pretty reasonable, like 30% plus versus a 3970X, and you make money with your computer, and getting projects done faster will be meaningful to your ability to bring in more jobs, then it's probably worth it. And if you don't, well, you might be able to just run with a chip that costs half the price. So that's it for this one. Thanks for watching. Our thanks to the unnamed YouTuber for sending out the 3990X so that we could basically pull it out of a box and put it under liquid nitrogen. That was insane, but we'll try and do more of that soon, probably with a different chip at that point, or we'll have to send it back and then request it again. But you all can continue trying to guess who sent it until they decide to come forward about it in the comments below. Post your guesses. It'll be fun to see if anyone gets it right, but I won't be able to tell you. So that's it for now. Subscribe for more. Go to store.gamersnexus.net to help us out directly, or patreon.com/gamersnexus, where you can get behind the scenes videos where we showed, for example, some of the early testing for this stuff before we even published this review. And then also check back for our factory tour series that's getting refreshed in the next week or two. I'll see you all next time.